we were talking about circular orbits and angular momentum. And I don't believe I have to do a full redress of what we talked about yesterday, but I think I would like to just, at least for a moment, call your attention back to something that we talked about. The object itself, and let's just go ahead and say planet and star. Is that okay for now? So we established yesterday that if the system were such that the mass of the planet were much greater than the mass of the, even I blew it. So let me try and be better. I said sun and planet. Mass of the star was much greater than the mass of the planet. Then this system orbits around the center of the star, right? Now, if that's not true, the system orbits about the mutual center of mass of the system. True enough? For a moment, let's consider that possibility just in this context. So if I draw a line that connects the two things together, and we consider that maybe there could be a situation where the center of mass was, say, here, then we'd have an R that would be related to the separation distance of the two. That'd be used in one place, perhaps in the M1, M2, G over R squared. That would be where that would be used. What am I referencing here? Force of gravity. So we actually know negative R hat, and this equals the force of gravity. Also, that R would be what we would use to discuss the amount of gravitational potential energy in the system. Because that's still based on the separation distance. But the orbit, I'd have to take and break this up into, say, R for the planet and maybe R for the star. Right, because the orbital radius is based on the center of mass. This system would oscillate around the center of mass. So here are some things that are implications of that. First, this system would have an angular speed, right, omega. That would be the same for both the star and the planet. Everybody got that okay? But that the planet, it would have a linear speed related to its radius, and the star would have a linear speed for its radius. The star is going in a smaller circle because it has a smaller radius, so it has a smaller linear speed. Does that make sense? And the planet's going to have a larger speed because it has a larger radius. But they both would have the same angular speed, so they'd be revolving around each other. That okay so far? Now, with that idea in mind, we could find the angular momentum of the system. It would be a two-object system, and we would say L equals I omega. We would have to figure out what the moment of inertia. You'd have 2 point masses that are oscillating, rotating about this point. It would be complicated, but not impossible. All good so far? I'm just trying to kind of give us this context. I didn't give us this context yesterday. We did a portion of this problem first semester. We found the center of mass between the Earth and the Moon and used that new value to figure out what the corrected time for the period of the Moon was. We found that this suggested the Moon would only be taking 27 days to orbit the Earth from what we had calculated the day before, which was closer to 28. This is way back in October. It's just been a long time since we did it. And then we realized why it's 28 days anyways, because the Moon had to move a little bit further for it to get back to the place where it would be full again, because the Earth has moved in the interim. Do you remember all that conversation? Boy, it's a long time ago. But it was a nice conversation. I enjoyed it. Now, here, and maybe one other thing, something like, I don't know, and tell me what. I missed this opportunity yesterday, and I'd like to take it today. If we put the system back to what we were talking about at the beginning, meaning I take the system and assume that the star is much greater in mass than the planet. When we do that, of course, saying that the mass of the star is much greater than the mass of the planet, that puts the center of rotation back at the center of the star. And therefore, our object has a velocity. Do me a favor, just because I want to make sure, can you take a minute and tell me what the what the velocity of the planet would be if we were to consider a radius in a situation like this? I just want you to take what I had written the V is for the planet. I'll give you a minute and I'll call on one of you. Direction. So yeah, let's put that as MP. So Alexander, what is it?
I got V equals root of MTG over R.
So for us, we would have to change this for this example. So MSG over R. Yeah. So is that a constant? Does it stay the same? Okay. Now, here's a couple things to think about. Here's how we know it stays the same. First, in order for that to change, there'd have to be an unbalanced force acting on the planet. And based on the fact that there is an unbalanced force acting on a planet, is that force capable of changing the speed of the planet? And we answered this yesterday, but if you don't know the answer, then it's just as good as not looking at your notes from yesterday. But the force on the planet is this way. And because it's perpendicular to the motion of the planet, there's no component of that force in the direction of motion. Therefore, it can only change the object's direction. So for this instance, although there is an unbalanced force on the planet, there isn't a force directed that is changing its speed. It's just changing the direction of the planet. At the same time, if we look at the value of the radius and the direction of the radius for the standpoint of talking about torque, does this force cause a torque on the planet? Now, if we look closely, we know it's going to be R cross F. That's how we calculate torque. We do have a clear torque arm, and we do have a clear force. I'm not going to put MP MSG over R squared there, but that would be the size of that force. But what is the angle between the radius and the force? It's either 0 or 180, depending on how you use it, right? Sine of 0 and sine of 180 both equal what? Which means that there is not a torque on the planet. That's why the angular momentum stays constant. Now, I said that yesterday, that the angular momentum stays constant as it goes around, but I think that's obvious. Because the velocity is constant, it makes sense that the angular momentum stays constant. And yesterday, I said that we had to use this to calculate angular momentum. It occurs to me, there's absolutely no reason we couldn't have used this to calculate the angular momentum of the planet. Now, the star, we're not talking about its angular momentum. We're talking about the angular momentum of the planet as it travels around the star. So I'm not including the star in this conversation. And I'm not really interested in the angular momentum that the planet might have because it's spinning. I'm talking about the angular momentum due to the orbit of the planet. Now, the truth is there's lots of ways this can become way complicated. Again, if I put my center of mass here, then I have an angular momentum due to the system oscillating around this point. But the planet and star probably have individual angular momentums as well because they're spinning. Stars spin and planets spin. So I'm trying to narrow down this conversation, which I did not make clear yesterday, that I'm only talking about the angular momentum of the planet due to its orbit around the star. Okay, so I'm trying to be very focused in that. Good so far? Because, for example, the Earth is spinning about the orbit here. But you would have been right to call me out about this, and I think one of you tried, and I just stomped right over you, that we should use this. But we could have used this. It would have been fine. And I didn't bother, but let's be clear. I told you that this could only be used when the object's traveling in a straight line, and it's not. It's traveling in a circle. So why do we use it? Because it's a point mass. And instantaneously, it has a velocity that is perpendicular to its radius. That's why we used it, and that's why we came up with, r times mv times the sine of 90 degrees. Right, that's what we did yesterday. But we just as easily could say that, well, the planet is a point mass. Therefore, its moment of inertia would be mr squared, right, from the standpoint of an axis of rotation at the star. Right? You guys see why I'm doing that? And omega is just, well, v over r. Right? It's like substitute v over r in for omega. And clearly, this works out to be mp times r times v. They are the same, just different order. But they're the same, right? That has to be true. They have to be in agreement. Now let's shift our conversation a bit. Most orbits aren't circular. Most orbits are elliptical. In fact, most orbits aren't even, don't have to even be stable, but planets generally have stable orbits. So objects in elliptical orbits. Now, we haven't studied them too much. We haven't talked about them very much, but an object traveling in an elliptical orbit still has many of the same qualities as an object traveling in a circular orbit. One of those qualities is that at any one time, the object's velocity is going to be tangent to the curve it's traveling on. However, there's only two places where its velocity is perpendicular to its radius. That's at a point that's furthest away and a point that's closest. We refer to that actually as apogee and perigee. So the point that is furthest away is called the apogee of the orbit, and the point that's closest is called the perigee of the orbit. It's vocabulary that's not necessary for you to know, but you want to be learned people, so sometimes knowing things is okay, even if it's not strictly because it's on a test. Some people believe that winter and summer are caused by the Earth being closer to the sun and further away from the sun, and that's not true at all. Although the Earth's orbit is slightly eccentric, it's pretty close to circular. Summer and winter are more about which part of the planet is tipped towards the sun. And that's what makes the difference. It's about the amount of light per square meter that strikes the planet that determines whether we're going to be cold or hot. So when you tip the part of us away from the sun, then we get less light per square meter, and that makes it more difficult for us to heat the atmosphere, and thus it's colder during those months. Now, this might not be obvious, but if you look closely, the force acting on the planet has to be along those green lines, correct? Because that's the line that connects the star and the planet together. And although it might not be clear to you, except for apogee and perigee, when we look at the size of those forces, they're not going to be the same for one. The force here is going to be much less than the force here because of the difference in distance. We know that the force of gravity is related to distance, and because when we're further away, we'll have less force. But if we're starting from the point that's the apogee, the far away point, this velocity, after this moment, there is a component of the force that's along the direction of motion because the force is no longer perfectly perpendicular to the velocity, which means the planet is speeding up as it goes from the farthest away point to the closest point. It's becoming faster and faster. So by the time it makes it to the point of the planet where it's closest, it's traveling at a much different speed than it was traveling when it was furthest away. So when the force is the strongest, the velocity is also the biggest. Now, the reverse of that is true as well. If we look at what's happening as the planet starts to move from perigee to apogee, there is a component of the force that is against the direction of motion. So the velocity is becoming less as we get further away. And although that force is getting less, it is slowing the planet down. So over here, we're traveling the slowest, which is good because the force of gravity is also the weakest force. Right? It's that force that turns the planet. So at that instant, the force is purely trying to change its direction because there's no component in the direction of motion. For that instant, doesn't have a tangential acceleration. When it's closest, same thing. It's traveling at its fastest. Right? It's no longer getting any faster. It's traveling at its fastest, but we have the greatest force. But one thing I want to point out, and let's use this one to point it out. The force of gravity is still towards the star, but our value for our torque arm, when it comes to torque, is still directed directly away from the star towards the planet. If we were to look at the net torque on the planet, that would still be R times F times the angle. Although there is an angle between the velocity and the star, this angle, remember, is the angle between the torque arm and the force. And do you notice that it's still 0? Or 180 degrees? Do you guys see that? We're talking about this direction and this direction. Is it clear that they're at 0 or 180 degrees? Which means that the torque on the planet is still 0. If there's no net torque on the planet, then the angular momentum has to be a constant. So even though R is changing and V is changing and the angle is changing, they're all changing in proportion to keep the angular momentum the same because the net torque is 0. That doesn't matter a whole lot in some of these because for a lot of these, we don't know the angle between the velocity and the radius. So like for here, I'm not sure how I could use that information. But one thing that should be pretty clear is that the angular momentum here is just going to be R at apogee times mass of satellite times V at apogee. And the angular momentum over here is going to be R at perigee times the mass of the satellite. I'm putting S there, and I've been saying planet the whole time, huh? Mr. Shelton should be consistent in his words. So mass of planet, and then V at perigee. So closest, furthest. If you know the speed at one, you can figure out the speed at both. Now, something else that's interesting is gravity is a conservative force. Because gravity is a conservative force, and there's no external forces on the system, the energy of the system must also be the same. It doesn't change. Now, granted, we have greater kinetic energy at some point, but we also have a bigger negative gravitational potential energy. So when we're here, the gravitational potential energy is more negative, but the planet is also traveling faster and has more kinetic energy. We're traveling here, the gravitational potential energy is not as big a negative number, but the kinetic energy is also smaller. And since there's no external force of the system, the potential energy plus the kinetic energy will also equal a constant. Now, this might not seem like much, but this is a system that has lots of equations and multiple unknowns, but consider it's going to be mass of star, mass of planet, G over R plus 1/2 mass of planet, V squared. With these two pieces of information, you can figure out the velocity of a planet anywhere in its orbit. This one can be used for any of the positions that we see here because it doesn't require any information about the direction of the planet. However, this one for us really can only be used at apogee and perigee. Otherwise, we need to know the velocity of the planet and the angle relative to the star. But, and I want to come full circle, this kind of stuff is asked on the AP exam. But they tend to focus on the apogee and perigee question, giving you information about what's happening at the perigee and asking you what's happening at the apogee, and then maybe asking about the energy of the system or showing that the energy is constant or something like that. It is certainly easier to set RMV equal to RMV when trying to figure out how the object's velocity changes between the closest point and the furthest point. Does that make sense? Now, that's an awful lot, so let me make sure I sum up the important details. First, the energy of an object in orbit stays constant, whether it's an elliptical orbit or whether it's a circular orbit. It's more complicated with elliptical, doesn't matter. Second, the angular momentum of an object in an elliptical orbit also stays the same. It's a constant. The net torque is 0, so the angular momentum is constant everywhere in its motion. You can use that to figure out how an object behaves at one location versus another location. Now, questions to this point. I mean, you probably don't know what to ask at this point or how I'm going to deal with this. So let me be very clear. This is it's not a footnote, but this represents like 2% of the content you're supposed to know for the exam. The way it gets used on the exam generally is in concert with some other things that we might know. If they have an orbit question, they're going to focus on apogee, perigee, and circular orbits. That's what they're going to focus on. So generally, they'll have a circular orbit portion of the problem, and then they'll say something like, but now the object's in an elliptical orbit, compare this state with this state. And it's going to be setting something about this point equal to something about that point. That's very much how they're probably going to phrase the problem. But I would like you to know a few other things here. So although all of this is stuff I want you to have in your head, I want to remind you that Kepler's laws are still at play here. Kepler didn't have Newton's laws to work from, and Kepler didn't have the knowledge that we have about the way these things interact. But Kepler came up with almost all of this on his own, using nothing but mathematics and observation. He said the same things about angular momentum and energy, but he didn't know about angular momentum and energy. So the way he said it, the way he predicted it, was different. He knew from observation what was happening. So Kepler's first law is that objects in orbit form elliptical orbits with the star at one focus. Remember, he was talking about stars and planets. So that's the first thing. You guys have done work in your math classes about conic sections. You're aware that an ellipse has two focuses, or two foci, and that the star will be at one of those foci. A circle just has two foci that overlap, right? It's a subset of ellipses is a circle. You guys also know what eccentricity is, right? Did you learn about eccentricity? I'm seeing some head shaking. That's okay. You're done writing these notes down, right? So an eccentric orbit is one in which the orbit is elliptical. So we describe eccentricity by looking at two factors. We take the semi-minor axis and the semi-major axis. We divide the semi-minor axis by the semi-major axis. That's the eccentricity of an orbit. I'm sorry, that's the eccentricity of an orbit. So get all that off of there. So the minor to the major. An eccentricity of 1 is a circle because the semi-minor axis, semi-major axis are the same. Most planets have an eccentricity that is less than 1. They might be very nearly circular. The Earth is very nearly circular, but it's slightly less than 1, like 0.99 something. Some have very eccentric orbits. Obviously, the squishier and longer it gets, the more eccentric it is. So comets, we tend to think of them. They have very eccentric orbits. So they tend to go very far away from the sun, come back every something hundreds of years. They are in very eccentric orbits. If you look at all of our planets, the more you get towards the outside of our solar system, the more eccentric the orbits tend to get. But there are some pretty interesting things in the small spaces when we talk about this too. But let me finish out Kepler. One of the other things Kepler did is he did talk about angular momentum, but he didn't have a word to use for angular momentum. What he said instead was, planets sweep out equal areas in equal time. So if you pick a time period and you look at the area that is swept out, so let's say the time to go from 1 to 2 is the same as the time to go from 3 to 4. Right? I didn't draw it this way, but what Kepler said is if the time is the same, then this area will be equal to this area. And what that should clearly indicate to you is that the planet travels faster when it's closer to the star and travels slower when it's further away from the star. That's the only way to make those areas equal. Kepler found that out mathematically. And I'm not going to play around with ellipses to prove that to you. I don't think I need to. We know the momentum is a constant. We know that because of torque. He found it out mathematically and stated it by talking about that. And then the last one is Kepler's law that we proved first semester, that there is a ratio that exists between the period of the orbit and the radius of the orbit, that the square of the period is proportional to the cube of the radius. We only saw that for circular orbits, but it ends up being true for all orbits, that the square of the period is proportional to the cube of the average radius. And he proved it again mathematically, looking at actual systems and watching them and observing them. So those are the three Kepler's laws. And they have been held as evidence of kind of the brain power. This guy figured it out by hand, no computers, through observations in a telescope, which I kind of think is pretty amazing. Of course, you had to dedicate dozens and dozens of years to those observations and get lots and lots of data to do so. But I guess if you're determined, you can be remembered for a long period of time. I'd say that's what he did. About its axis, the Earth on its own, would have an angular momentum that would probably be relative to 2/5 mr squared, where this is the radius of the Earth. If I just assume the Earth is a solid sphere, which it is not, but we're just generalizing, times omega, which is going to have something to do with the fact that it takes 24 hours to go around once. Right, we could calculate this value. This is an immense value. The Earth has a huge amount of angular momentum, which is why it's probably going to keep spinning for a long time. Lots of inertia. Now, that angular momentum, I'm leaving out of the conversation because A, it's not necessary to talk about orbits. This is not affecting the orbit of the object. And B, the Earth isn't a sphere. The Earth is squashed. It's bulgier at the center than it is at the top. Its equatorial radius is different than its polar radius. And the whole thing isn't spinning the same speed. We've got a liquidy, chewy center, and it's churning around in there, and its speed of rotation is slightly different than the speed of rotation of the crust, and it's a mess. So I don't want to talk about it. It's a mess. It's complicated. We could simplify it. It's just not necessary.